Welcome to the lecture series of network theory. We have already started learning the application of different important network theorems in DC circuits. In today's class also we will be learning about some other network theorem, which is maximum power transfer theorem in case of DC circuits. So first we will learn that what this theorem states, then we will learn that how to apply this theorem to simplify electrical networks or circuits. As per this theorem, a resistive load connected to a DC network receives maximum power when the load resistance is equal to the internal resistance or Thevenin's equivalent resistance of the source network as seen from the load terminals. Now we will understand this theorem with a real circuit. Now in this DC network, as we can see, we have 5 resistances or 5 passive elements, and we have 2 energy sources, one voltage source and one current source. Now in this network, if we choose this RL as our load resistor, and if we want to find out that how much power this load resistor will consume or absorb from the network, then that can be easily obtained by applying maximum power transfer theorem. Now in this circuit, if we want to get that what is the condition when this load resistor RL will consume or absorb maximum power and how much will be that power, then that can be easily done by representing the source network by its equivalent Thevenin circuit. So here, as we can see, that between AB terminals this RL is connected, and other than this RL, the rest of the network or the source network is represented by a single voltage source, which is Thevenin's equivalent voltage, and a resistance, which is Thevenin's equivalent resistance or internal resistance of the network or source network, and they are connected in series. Now if we connect back the load resistor with that series connection, then this is the modified circuit that we can easily use to get the condition and also the maximum power which is absorbed by this load resistor. Now from this circuit we can easily find out the current value, which will be already we have seen in case of Thevenin's theorem, that I will be simply VTH divided by the total resistance, which is RTH plus RL. Now if we want to find out the maximum power absorbed by this load resistor, that will be simply I square multiplied by that load resistance value. So I here will be replaced by this value, VTH divided by RTH plus RL, and whole square multiplied by the resistance value, and that is the maximum power delivered to that load resistor or absorbed by that load resistor. Now here, the condition that we will use to get the resistance value when that will consume maximum power, that is dPL by dRL, will be equal to 0, because here the resistor that we have used is variable. So we can vary the resistance value, or we can tune that resistance value till the moment when it will consume the maximum power. So when we will vary that resistance value, the power consumed by the resistance will vary. So there will be a moment when even if we change the resistance value, the power delivered to that resistance will change, but the change in power with respect to change in resistance value will not change. So the rate of change of power with respect to that resistance value will be 0. So that will be the condition that we will use to get the resistance value when that will consume maximum power. Now here again the expression of power delivered has been written. Now we will use the condition that is dPL by dRL. So before using that condition, which will be equal to 0, we will find out that what will be that value. So here we have differentiated this expression with respect to RL. Here RL is the variable, and in this expression of PL, as we can see that in the denominator we have RTH plus RL, that means we have that term RL which is variable here, and in the numerator also we have the term VTH square multiplied by RL. That means in the numerator also we have that variable term RL. Here the formula of differentiation that we have used, that is d by dt u by v, where u and v both are the functions of t. So if we have the division of these two functions u and v, then the formula or the rule that we know, that will be v multiplied by du by dt minus u dv by dt, and the whole thing is divided by v square. So this formula or rule we have used to find out the rate of change of power. So here RTH plus RL we have in the denominator, so it's square of that term. Already it was a square value, and so square of that square value. And in the numerator we have v multiplied by du by dt. So here v means RTH plus RL, that square. So here it is v. Then d by dt, here in place of t we have the variable RL, and in the numerator we have Vt square RL, and that is here u. So it is d by drl Vth square multiplied by RL minus u dv by dt. So here it is u directly has been written, and then d by drl, and then the v as we have already seen that v is this term square value. So this is. Now if we simplify further, then we will get, here it will be to the power 4 RTH plus RL to the power 4, and in the numerator if we differentiate this term, then VTH square, VTH is a constant term, so it will come out of this differentiation, and then we will have DRL by DRL, which will be 1. So this is the term that we already had, and then VTH square minus then VTH square, that term multiplied by RL we already had in the numerator, in the second part of the numerator, and then we are differentiating this term. So as per the rule of differentiation, it will be 2d RTH plus RL, and then we will differentiate this term separately. So RTH is constant, so when we will differentiate this RTH with respect to RL, then it will be 0, and DRL by DRL, it will give you 1. So this is the term that we will get in the numerator after simplification. Now if we simplify further, then it will be, as we can see in the numerator, we have VTH square and RTH plus RL. This term is common between these two parts in the numerator. So we will take VT square multiplied by RTH plus RL common in the numerator. So what will remain within the bracket is RTH plus RL from the first part minus 2RL. Now if we simplify further, then we will get this expression VTH square, then RTH plus RL, and in the denominator we have RTH plus RL to the power 4. So in the denominator we will have Q now, and in the numerator we have RTH minus 2RL plus RL, so it will be RTH minus RL. So this is the final expression of this dPL by dRL, the first derivative of power with respect to the load resistor. Now the condition that we will use is we will equate that to 0 to get the resistance value when the maximum power will be delivered. And if we do that, then the numerator will be equal to 0, and from there we will get RTH minus RL, that will be equal to 0. So the condition is RTH will be equal to RL. That means the load resistance value will be equal to the Thevenin's equivalent resistance or internal resistance of the source network. And this is the moment when this load resistor will absorb maximum power from the source. Now if we want to know further that what will be the maximum power value, then we can easily find out from this expression, like P maximum power will be the power expression is I square R. So here I square value, the value of current that will flow through that load resistor, that we have already seen, and that value is VTH divided by RTH plus RL, and that square value. So it will be VTH square, then RTH plus RTH RL square, and since when the load resistor will absorb maximum power, the RL will be equal to RTH, and that's why in place of RL the RTH has been written here. And here in the numerator also we will have RL, because we are finding out the power absorbed by the load register. So initially it will be RL, and since this RL is equal to RTH, so that's why here RTH has been written. Now if we simplify this, then finally we will get this value VTH square divided by 4 RTH, and that is the maximum power value absorbed by that load register. Now in the modified circuit, we will have one resistor and one voltage source which will represent the source network, and then we connect back the load register. Here this value of this voltage source will be VTH, and the value of this internal resistance or equivalent resistance will be RTH. And when the load register will consume maximum power, then the value of that load register will be also RTH, and the power which will be consumed by this load register is this that we have already derived. Now by this load register also, the power which will be absorbed, that will also have this value, because there also we will use the same formula, I square multiplied by the resistance value. So I have this value only and multiplied by RTH. Finally we will get this value only. The total power absorbed by these two resistances will be twice of this value. So here that has been shown. So the total power will be this. That means the power absorbed by the load register, or the maximum power absorbed by the load register, will be half of the total power. So if we want to know, or if we want to calculate the efficiency when the load register absorbs maximum power, that will be 50%, as it consumes half of the total power. So this was the derivation of the condition when the load register will consume maximum power and how much power it will consume. Now next we will see in step-by-step manner that how we can simplify the circuit to get those values. Now here the same circuit has been used. So what we will do in the first step is we will remove the load register, and we will find out the Thevenin's equivalent or internal resistance of the source network when we will be looking from the open circuited load terminal. So in the first step we will remove this load register. So after removing this load register, say these are the two terminals AB, we will look at the circuit from this side, and we will deactivate all the energy sources the way we do to get the Thevenin's equivalent resistance value. So voltage source will be simply shorted if it doesn't have any internal resistance, and the current source will be simply open circuited if it doesn't have any internal resistance. Then we will find out the equivalent resistance with respect to these two terminals. So for this circuit, it will be simply these two resistances are in series, so R1 plus R2, and with that equivalent resistance, this R4 is in parallel, and accordingly we will find out the equivalent resistance value. Then after getting this equivalent resistance, in the next step we will find out the open circuited voltage the way we find out in case of Thevenin's theorem. So with respect to these two terminals, we will find out the open circuit voltage, and that will be Thevenin's equivalent voltage as we know. So in the next step we will find out VOC value by applying the conventional circuit analysis method that we know, KVL, KCL, or whatever is suitable for this circuit. And then after obtaining that VOC, we will redraw the circuit where we will have VTH and RTH to represent the source network, and then we will connect back the load register with that Thevenin's equivalent circuit. The condition of maximum power transfer theorem, as we know, that will be RL will be equal to RTH, and after getting this circuit we will find out the value of current that will be flowing through this load register, and from there, or by using that current value, we will finally obtain the maximum power value that will be absorbed by the load register, or we can say maximum power which will be transferred to the load, and that is VTH square divided by 4 RTH. Now next we will simplify a DC network by applying maximum power transfer theorem, and we will see that how much power will be consumed by this load register, or how much maximum power will be transferred to this load register. So let's assume that this load register is connected between these two terminals. So in the first step we will remove that load register, and either we will find out the VOC or the Thevenin's equivalent resistance by deactivating the energy sources. Here first we will find out the open circuited voltage, that is VOC or VTH, and then we will find out the internal resistance. Here as we can see, this has a complete loop, so by applying KVL we can find out the voltage drop across this resistor, and when we will get that value we can easily find out VOC. So if we apply KVL in this closed loop or path, it will give us the equation like -8. If we suppose start traversing from this point, then from negative to positive, if we assume that as our negative voltage, then -8, then plus 2i, then plus again 2i, then plus 3 volt, so 3, and then we have 1 multiplied by I, that means I, and that will be equal to 0. That means from here we will get 5i minus 5, that will be equal to 0. That means the current which will be flowing in that loop, that will be simply 1 ampere. So the voltage which will be dropped across this 1 ohm resistor, that will also have 1, or that will be 1 volt. Now if we want to find out this value VOC, we can do this way. Now say if we think of this as a closed path, and if we start traversing from this point, then from plus to minus it will be plus VOC, then from minus to plus it will be minus 10 volt, then from with respect to this current, the current, since it was flowing in downward direction, so it will be, this will be at higher potential, this will be at lower potential. So with respect to the direction of that current, the polarity of the voltage drop will be like this, and when we will traverse in this direction, so it will be minus to plus, so we will take that voltage as negative voltage, so that will be -1, and the algebraic sum will be equal to 0. So VOC will be 11 volt. That means VTH in our simplified circuit will be 11 volt. Now if we remove, or if we deactivate all the energy sources from this circuit, then we will be left with only 3 resistances. So between these two terminals, or with respect to those two terminals, if we want to find out the equivalent resistance, then we have to look from this side, and the equivalent resistance value will be 2 plus 2, since these two are connected in series, and with that this 1 ohm is in parallel. So the RTH value will be simply 4, and then with that 1 is in parallel, so it will be 4 divided by 4 plus 1, 5 ohm. So in our modified circuit we will have this type of resistance RTH, then we will have VTH in series, and if we connect back the load resistor which has the value R that we assumed, so in this modified circuit, this VTH will have value 11 volt, this RTH will have value 4 by 5, and for maximum power transfer to that load resistor, the condition will be R will be equal to RTH, that means 4 by 5 ohm, and the maximum power transfer value, that will be simply VTH square divided by 4 RTH. So if we put those values, that means 11 square divided by 4 multiplied by 4 by 5, then finally we'll get the value as 37.81 watt. So this is the way how we can apply maximum power transfer theorem to get the value of maximum power transferred to a particular resistor. In my next class, I will discuss about some other important theorem. So with this, I end today's class. Thank you.